Hello, everyone. So welcome back. This will be the last in this big data series, at least for this semester. Um, so I thought what way to end this project by talking about what we were initially hoping to do, which is machine learning. So I'm just gonna go flip to a PowerPoint. So just gonna get started with it. So when we think of machine learning, we often think about computers making decisions for us by learning from the data and crafting their decision around it, which is just essentially a bunch of mathematical models meant to model data. And I found this really neat picture, which shows part of that process, which is a correlation plot. Typically, this is done to determine whether variables influence each other. So colors are according to how well they correlate. So it's not an R squared value, but it's how well they correlate. With zero meaning that honestly it's chance whether they correlate or not. Like the computer can't determine. Negative one is they really have no influence on each other. There's no way they have any relationship. It's not negative, not positive. And one means negative or positive. They correlate very strongly. It makes sense that down this area they're going to correlate very strong. And it seems like what's this one? Residual sugar and density. I'm not sure what this is. I assume it's from fruits or types of wines. It seems that these two correlate well together. As in the density increases, residual sugar increases or decreases more often than not. And what the computer can do is take this data set. I'm going to assume it's maybe thousands, 10,000s. It runs these linear models or whatever model you determine, and it takes that significance value and those correlation coefficients, does this a million times. It subsets data sets. So you can imagine your data set has 50 rows. It takes random subsets. So like maybe they take half those rows, random 25 rows every time to run these models. And now you're understanding what the computer does. And if you do the permutations, there are over, I believe, for 20 rows, there are 20 factorial combinations. That is just if they do one row at a time. Like they can do 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You get my point. There are more combinations than you could fathom, and that's why it's called machine learning. It is technically learning. It is figuring out these models, making these complex models that we cannot begin to comprehend. Um, and yeah, that's essentially what machine learning is, just correlations upon correlations upon correlations. And this is one step in it, which tells us which variables influence each other. And now this is what we call feature selection. This is step one in feature selection, which tells us, hey, which variables are super important? And depending on your purpose, you might say, hey, this residual sugar variable is important. It seems to be influencing density. It seems to be influencing a whole bunch of these. But what the computer can do is say, hey, this influences it, but it's not really that important. Maybe it's just a variable that's in there and it's causing all these influences. But what if we took it out? And the computer can actually take it out by doing more significant tests. And this is one feature of it. So ignore part A. I'm not sure what paper this is from, but part B is the only important part in my opinion. And this is an older type of graph. It's showing your R squared indicating significance, where things that are closer to the left you can consider as more important. This is opposed to most ones where importance is shown as a horizontal bar with more importance on the right, but this case more importance is closer to the y-axis. And it's plotting it as a function of R squared, and it seems to be these variables are picked and then they are within R squared. This is one type of a variable importance plot. It seems to be that this F4 is more significant. In this case, R squared isn't quite what R squared usually means in linear terms, but this is one example variable importance plot. One of my favorite forms of machine learning is called Boruda feature selection. So Boruda feature selection. It essentially takes features of your data set. Let's say each column could be a variable. Variables are also called features in machine learning. It takes each one of those and it tells you how important it is from 0 to 10, 0 to 100. But what it means is that things in the green, pretty important. I think moreover, those have to do with just how big their error range is or where their mean's located. It really is iffy. I'm not too sure about the mechanism, but I know green essentially is zone 1. It's variables that are pretty important. Yellow is zone 2, not important. Red means they're probably not important. They're probably more likely just chance. So yeah, this is essentially what the graph outputs, and I will show you. You'll get a graph that looks very, very, very similar to this. Yeah. So what does Boruta do? So let's say we have 5 rows, and this is your data: age, height, and weight. What it's going to do is it's going to generate random numbers, totally random numbers, simulating this data set. So they're not completely random. What they do is they randomly shuffle the variables around. They just generate numbers that kind of are within the range of values provided. So they look real. Like, these make sense. Like, I don't necessarily know of, I'm trying to think of a good example. They just shuffle around essentially. Sometimes it's random. In this case, it seems like it's not randomly, but they're usually just shuffled around. So you can see 51, 176, 75 is totally unique. And what it does is it does feature selection. It generates this plot essentially. You can think of it that way. And then it compares the plots for the original data set, and then when they shuffled around. Variables that are significant, aka variables that are closer to this, left-handed side, they're gonna keep it. They're gonna keep them, and it's gonna say feature importance. It's gonna quantify it for us. It's gonna do some calculation. It's gonna tell us how important it is, which I think is very neat. But feature importance isn't, as a percentage, not important, especially when you only do it for one run. And it seems like age and height hit once, which means that they were deemed significant. It seems that weight hit 0 times. And it seems like these ones did not really matter, because obviously these are the ones that are randomly shuffled. If these got a hit, then you can automatically toss out your data set. In fact, you can probably assume your data set is not significant. It's garbage. Okay, so to clarify, shadow and these variables are just a shuffled around variables the computer did completely randomly. And if they ever hit, and if they ever were deemed important and hit, that would be a big problem for us. Okay, so if you run this data set a couple hundred times, or in this case 20 times, it seems like these shadow variables are no longer significant. And it seems like you just get these hits. Hits meaning how many times the computer found that these variables popped out a couple times in their significance. Seems like weight rarely did, height did a couple times, age did too. And essentially what's going to happen is that you can think of it like a bell curve, where age, the variable that hit a lot, is up there. It's features to keep. And then ones that are tentative to keep, like height's among them, doesn't really hit that often. And weight's not important at all. You can forget weight. So it's going to drop it from the model. And you do this a couple hundred times with bigger data sets, you're going to get something like this. This is from a real patient data set. As you can see, it looks like age followed by your estimated glomerular filtration rate seems to be the most important, as you can see, and then all the rest drop off. Now, this is actually from my paper, and it's actually something that's really hot and spoken about in the literature for these machine learning models that, sure, you can do a regression. You can do a whole bunch of generating data. You can do variable importance, all that stuff. So not variable importance, but you can do all these tests to tell you significance. And it'll just tell you, hey, within 0.05 or 0.01, whatever your confidence interval is set at. But is it really important to determining my outcome? In this case, I set my outcome for this to be mortality, all-cause mortality. So what it did is it said, forget significance. Is this variable really that important? And the red ones obviously are not. It seems like a majority of the patient variables collected are not important. Let's pull one out. Ethnicity seems to not be very important in determining mortality, which goes against our thinking, but the machine learning results in this data set invalidated the conclusion they are important. They not validate it, they invalidate it. Seems like these green ones, though, especially my hypothesis, was supported. So I cut this down to make it look pretty, and that's the graph you saw in probably one of the intro slides for this little course. And this has actually this is going to be accepted to a conference, and it's currently in a manuscript that's going to be sent to publication. So this graph, as simple as it may be, condensed down all this information, which to a statistician is quite important. And to an engineer was very important. You can imagine this could be anything from bacteria size if you're testing some BME things, or polymerization times, a whole bunch of things this could be. I simplified it down for the clinicians. You modify the data to fit the purpose, and I did it in this case as well. Okay, so that's the theory behind it. So not really mathematical. There's no good way of explaining it mathematically by hand. I will link a video to one I made last year, which explains another form of machine learning called random forests, which seems to be more popular. But I'll just summarize some new things. I added this. I did make this require, so I'll export this and send it to you guys through email. I had this Boruda package. Only the thing I changed my hypothesis. I made it so that people with a BMI over 30 were included in my filtered data. I'll just run it to show you what it generates. It's quite interesting, actually. So as expected, there's some stuff that changes. I also cut down the variables. So I added this little select command before I create the table, just so I could make it into a nice little thing to show you. Seems like systolic, 105. So 0 means dead. Sorry, 0 means alive, 1 means dead. You get the point. Looks like stuff does change. The average age increases significantly for the people that are still alive. And then, yeah. Moving forward, I did the same thing for the Kaplan-Meiers. It looks like, some stuff changes, but not really that significantly. I did some hazards as always, and it seems like I will rerun it for our purposes, but it seems like the hazard ratios do change. Pretty significantly. They change a lot. Seems like hypertension is much more important in determining all-cause mortality in people with obesity than people without obesity. It also seems like age is a more determining factor. It seems like this congestive heart failure is more important. It seems like this one, which I believe could be myocardial infarction, is important for people without obesity, but with obesity, it doesn't really matter. This 95% confidence interval is pretty large. And as you're more obese, it seems like your BMI determines your mortality versus, yeah, it's a little confusing how to interpret that one. It's a continuous variable, and that is past the purview of this course, but interpret how you will. There's whole courses dedicated to this at Case in the population and quantitative health sciences departments. But yeah. And then the new stuff I added was this stuff. So this I copy pasted from the help package, if you will, for the Boruda, like the little help. So when you run it, you get a couple things. So console stuff, which I did this do trace 2 to tell me what's happening. Seems like around 100 iterations determine variable importance. So on the surface level, this is quite not really relevant. This stuff I already knew. Age is the single most important factor in people without obesity, or people in the total data set, including obesity. This is the first one. Second one, just obesity. And it seems like systolic is important. It seems like these ones shuffle around somewhat, and this is significant. You can zoom in if you'd like, by opening this a different tab and magnifying. You will see these all are significant compared to one another, and you see there are colors, like obviously they were green, etc. This is variable importance. So this is now we know how to do the coding, and I'll explain a little further how I did it. So I took the big data set and I selected for the variables I'm interested in. These are the ones I selected based off this little code book I made up here. I just shuffled them around as well. I Googled some, added some, etc. And I say data set original, select for that, make it a new data set. And then I do this Boruda. This is just making a variable of the name Boruda. This command, just don't change. This is the data set you want to use. And then you don't really need this. I'm actually going to highlight it out. This is more for diagnostic purposes. This just basically tells you, hey, what variables are significant, etc. And this is actual plot command to plot those plots. So that's a really overview of the whole features. What I want you guys to do, and this is actually going to be part of the final project. This is all you need to do for the end of November. All you got to do is test your own hypothesis. I want you to create different tables, different Kaplan-Meiers, and I really want different Borudas. Play around the titles, look up help stuff. There's a whole bunch of things you can do. I want you to test a different hypothesis. Maybe you want to test, hey, people with certain blood pressure range, or people with high cholesterol, or whatever. I have given you all the information you need. In fact, all these previous videos, I explained everything you could do to test your own unique hypothesis. And you know what? Maybe you discover something new and novel, and maybe you want to get this published. And you can most certainly do that. In fact, talk to any professor and they will jump on this because very few people are skilled enough or even willing to look at this type of data anymore. You can Google the NHANES data set. Not much research has been done on it since I think this came out. I don't think in the last decade there's been maybe more than 50 papers about it. So you can do the math, maybe like 5 a year, and they're all over the place. I focused more on the clinical side, some focus on the more mineral, chemical side, a whole bunch of things you could do with this data. So I want you to make a nice little thing. So how do I get these tables in here? Well, I hit this knit button up here. When you hit knit, it'll do this R markdown. It might ask you to install packages, go for it. And when you run it, it'll go through a whole bunch of commands. And we'll let it sit here until it finishes. It should take a couple minutes. You can feel free to skip past this point. But yeah. As you can see, code finished. Open this nice, I guess HTML in my case, but you can open a PDF and it gives you all the output, but more importantly, it gives you these graphs and you can just take it as a picture. You don't have to screenshot or anything. It's like a high resolution picture. That's how I got those in this Word document. It works for, I think, every one of these, but even this one. I believe it works for the tables if I can find them. Yeah, these tables. Oh, I think the tables just got a screenshot, or you can copy paste. Totally up to you. But yeah, that's essentially what I did. And then I put them here. And what I want you to do is, you can like give me like a nice little title, put your name, provide me a brief introduction as to, reasons for analysis, i.e., you could say, I am interested in testing BMI versus all-cause mortality. And you could say, maybe, you know what, you could even go further and write a formal hypothesis. People with a higher BMI are more prone or more vulnerable to comorbidities, which is supported based off the fact that hazard ratios for like congestive heart failure were higher in people with a higher BMI. Makes sense. More risk for dying from same conditions as a normal population. Go a step further, make it a control population with the big overall data set. What you can do is instead of filtering and making this a separate data set, you filter and set it to the opposite range. And what you can do is make it a proper control in that case, which would be nice. And then you can actually make it more comparable. You can do what I did, which is the lazy way, or you could do the better way. And then you could, show some data, explain the data a little bit, make some nice captions. And you know what? If it's good enough, we will actually submit this to maybe a grant or something to make this part of the university's curriculum for undergraduates. You might end up in a paper here or there, so you never know. And then this data, you guys can feel free to use this for any purpose you'd like. I'm not going to restrict you and say, hey, you're not allowed to use my data. I really don't mind. I've exhausted this for my purpose. As you can see, I literally have the same data sets with 101,000 patients. Like I've combined them over the years because this NHANES data set spans, I think, 20 years. I just did it for 1 year, which should be, I think, around 10,000 patients. So yes. So essentially what I want you guys to do is watch. I'm going to give you another video, which covers a little bit of a different approach. I actually did not use patient data. I used medical donations. So more pertinent to MedWish's purposes, but less interesting in my opinion. I ran machine learning on that and a whole bunch of stuff. I will send those as YouTube vids. Let's see. Watch this one, of course. Finish this one up. Run through my code, read it, make sense, and then test your own hypothesis. In fact, you know what? You can even delete all the stuff I've written. You can make it look pretty. You can play around with the formatting. You can Google such as R Markdown, which is the package that uses this knit command. or you can Google knit R and like figure out how to make it look pretty and yeah, explore, have fun. And once you finish it, whenever you're happy with this, turn it into me, send me an email, and we will count you as a finishing a project and being one step closer to being an official member of the club. And if you want to explore this further, please feel free to email me. I'm happy to discuss coding over email. We can talk about whether you want to get this into a paper. Um, I'm not going to claim responsibility. This is the code I've given you. This is open access. I really don't mind. Use it for any purpose you'd like, and hopefully you get a publication out of it. But that is everything. I will send the slides, all my code, my previous YouTube videos, and all my previous codes for you guys to explore and look at. And feel free to adapt to your own purpose and have fun with this project. Anyways, have a good week, guys.